Really excited to welcome Angela, who came in from New York. She works at Meta AI on a lot of large language model work, and particularly for machine translation. And yeah, really excited to hear what she has to say and all the work that Meta's been doing recently, which is very exciting. So, thank you. There you go.
Hi everyone, I am so excited to be here today. I battled the Eurostar and food poisoning, and I've not thrown up in 3 hours, so we are here for this, so yay! So thank you all so much for being here with me today. So I want to talk a little bit about translation. So we're very, very hype about Gen AI today, and I know we're all about the decoder language models. But to me, some of the greatest commercial and widespread applications of AI have come through things like translation, which is type of generative AI, but with sequence to sequence rather than decoder only. And I know for me myself, I would never have been able to battle through all the French government paperwork without translation. And so it's really important that we keep the quality high. So something that we started thinking a lot about at Meta maybe 2 years back is kind of the volume of different languages worldwide. So there are thousands of spoken languages, and there's more than 3,000 written languages today. But if you think about a lot of commercially available translation systems like the ones that we use, they actually only cover a small fraction of these. So these numbers are slightly outdated. They're from around last year, around this time, I think. But Google Translate and Microsoft Translate, which are some of the top used translation systems, only cover around 100 to 130 languages. And so one of the things that we started thinking about was many of us working at Meta actually speak some languages that are not covered. So actually English is my third language, and my native language is one that doesn't even actually have a formal writing system. And so we started talking a lot about hey, a lot of us are working in NLP research. What is something that means a lot to us individually? And so a lot of us got together and started thinking, okay, let's work on developing translation systems that cover more languages. And so we started with something very, very simple. I know there's 3,000 languages, but let's just try to double this, right? Double the coverage from around 100 to 200 languages. And then we were okay, well, let's start here, and then we can go from there, and we'll see if it's easy. We can always scale up. Turns out just 200 is pretty difficult. So I'm going to talk today about the journey to get there. And of course, you can say that your model covers many languages, but of course, we're really talking about high quality, safe translations that people could actually use. So before I get into some of the work that we did, I want to cover a little bit about the current progress in translation. And so there's been historically a lot of focus on higher resource languages. Actually, a lot of work has been done on European languages, partially because of the Europarl data, which comes from European Parliament. And so that served as a great training data set for a lot of progress in translation. But more recently, there's been a lot of focus on lower resource languages. And a lot of it has come through the development of new data sets. A lot of criticisms of these developed data sets, usually by people who speak those languages, being not sure it's actually in this language. And of course, work on new languages. And something I find really exciting about the research community now is a lot of people who speak these languages have started working on technology that works for them as well. And so I want to cover today very briefly our approach, some of the data that we developed and open sourced, as well as our open source models and some of the techniques that made this possible. And I want to also end with some discussion about evaluation and how we actually talk and think about the quality of these models. So starting with our approach, I think the first biggest problem that I think about a lot when starting a new research project is how do we know we're working on a real problem? And so before I worked on translation, I worked on on-device AI, and it turns out I was a couple orders of magnitude off in my estimation of how small models needed to get when I talked to some of the actual teams that were putting models on device, for example, in WhatsApp. And so I was okay, we gotta do this properly. And so one of the first things we did was we actually took a very social sciences approach, and we worked with different sociologists to conduct interviews with low resource speakers of different languages all over the world. And so we tackled about 36 different languages globally and had interviews with about 44 different native speakers. A lot of them were immigrants, And so they had the experience of how difficult it was to learn a new language and relied heavily on translation technology. And some of the most important findings was that people were pretty scared that their languages were going into a state of decline, even though they were spoken by millions. So my native language is spoken by 14 million people, but the younger generation, actually, it's not taught in schools, and so it's probably going to disappear for, I guess, if I ever have kids. There's also a lot of excitement about being included in existing translation systems. So I guess if you're listening to this talk, hopefully you speak and understand English. And so we're part of the privileged group where technology is really often developed first for English speakers. And so everything kind of works out of the box, right? Like GPT works for us, DALL-E works for us. And so we're kind of like always with this type of technology. But for many people in the world, this technology doesn't work for them. And sometimes like even years later, it won't. And however, we also talked to them about, your language might be supported in Google Translate today or Microsoft Translate today. Like, do you find the quality sufficient? And I find this one very funny because since my parents know that I work on translation and they get what translation is, they're always like texting me examples of like where Google Translate got it wrong. For Chinese, like Mandarin Chinese, which is probably one of the most worked on languages in translation systems today. And so most people find that quality is largely insufficient for reliable usage. Like you wouldn't want to translate an important document with Google Translate. So I want to talk about some of the biggest limiting factors. And so as with all machine learning, translation is powered by data, and so we got to start here. I want to talk first about evaluation, because I think we talk a lot about training and producing systems, but most important is to understand if your system is good or not. And so we came up with this data set called Flores 200. As with all research, it was a very iterative process that we built up over a number of years. So we first started many, many years ago with just 2 languages, Nepali and Sinhala, and we extended that to 4, and then we extended it to 100, and as part of this, we extended it to 200 languages. And so this is a machine translation evaluation data set, although you can use it broadly for other things. There's people using it for language model evaluation now, for example. And it has a deep focus on low resource languages. It's properly many-to-many, which means that all of the sentences were originally in English, and then they were translated to all of the different languages. And so you can measure the quality of translation from like Bengali to Chinese, for example, because it's fully aligned. It covers 200 languages. I guess that's in the name. There's a wide diversity of different domains and topics. I think this has been an issue that has plagued some of translation research. So if you look at a lot of translation data sets, like measure the quality of news translation, or we have like a biomedical translation data set, but you don't really cover the span of content that actual people want to translate, because most people are not just translating news articles. And so the way we develop this is in a multi-step process. So the first thing we do is that we take the document that needs to be translated, and we work with a group of professional translators who are certified to speak their language. They produce translations. Then we do some like automatic checking, if the input sentence was like 20 words and the translation is 1 word, it's probably not a translation, right? So there's like some automatic checking that we do. And then we have an independent, separate set of translators to do quality control and quality assurance. And these 2 groups need to agree on the quality. And if they don't agree, it gets sent back for translation. And this kind of step is really important to ensure the quality stays high. If they don't agree, there's a post-editing step. And then finally, the quality check, if it passes like a 90% bar, then we consider the translation complete. So there's a lot of challenges in this process, which is partially why like the translation process is so complicated. The first one is for many languages, it's very difficult to find translators. So when we were working on Tonga, the internet was not working in Tonga for like a wide span of the project. And so it was just not possible to find a native Tonga speaker. So it was not possible. Then there's other issues in language standardization. So for example, French translation, there's standards for how you should be doing French translation, but for many of these lower resource languages or that are more colloquial, there are not standards for how you should translate, for example, like scientific or encyclopedia content. And so it's really important to kind of align and get groups of translators together to figure out, like, okay, what's happening. A good example of this one is actually Breton. If you're from France, there's two competing standards of Breton, and they don't like each other very much. And so it was extremely difficult to reconcile this. And finally, I think a lot of these languages actually have multiple different variants. So there are some languages like Santali that were traditionally written in one script, and now the government is trying to switch to another script. And so it's actually quite difficult because people are naturally writing the same language in multiple different ways. And we need to represent all of this. So assuming our evaluation data set is created, I want to talk now about how we made the training data set. And so training data for these languages does not exist naturally. And you could sit down and pay like translators for like a decade or something to collect the volume required. But we tried to do this in a more scalable method. And so we used a method of mining that we started many years ago in the Wikimatrix project, where we tried to match different sentences across various languages in Wikipedia. Then we moved to CC Matrix, which does this in the web. And then we had this work, I think back in 2019, that tried to do this, extending it to 100 languages. And so the way this approach works is based on sentence alignment. So we take a bunch of data from the web, Common Crawl, which is probably very widely known because of all of the work in language modeling. We extract all of the text, like ditching all of the HTML, all of the noise, really try to clean it out, and then we split it all into sentences. And then we embed these with different encoder models, and then we try to find matching content that could be a translation. So the way these encoders work is that we put these sentences into high-dimensional vector space, and then we say sentences that are close in this vector space in different languages, when they overlap, then we say that, OK, this content could be a translation. And so the biggest challenge is, how do you train an encoder model that properly represents these languages when there's like very little training data? And so there's two techniques that we did that improve upon previous work. The first one is using mass language modeling. I guess now in 2023, this is not like a new thing. At the time, it was one of the first works. And the second one is using multilingual distillation. So we tried to use a teacher model that covered more languages and distilled it into various smaller language families for students. And this is because, for example, Cyrillic languages can learn from each other. And so even though some languages have less data than other larger languages, by grouping them and using a teacher model to teach a student model, you can get much higher quality. And so just an example of the quality. So the y-axis here is the error rate. So lower is better. And the x-axis is a wide variety of different languages. So for example, AMH is Amharic. And so the gray bars represent the error rate of the previous laser model. So this was a model that encoder, sentence encoder model, multilingual, represented 93 different languages, and we released it. Turns out it didn't work very well for many languages, as you can see from the high error rate. But the model that we used and released with this work, Laser 3, it's represented by the blue bars, which you can't really see too much here. So how does this all come together in the final data pipeline? Like how does it all work? So we do language identification on the training data. We actually use human evaluation to train our language identification systems. So this allows us to clean our web corpora. So if you get a page of Common Crawl, like what language is it in, you gotta label it somewhat correctly before you can do your training data. Then we use our laser model to do by-text mining, and then we finally validate the quality of our models with small bilingual machine translation models, which means that we take this training data and we create a bunch of small machine translation models to measure the quality. Obviously, this pipeline is very complicated, but don't worry, there's an open source library that reproduces all of it. Now I want to talk a little bit about the modeling techniques. So why is this so difficult? Well, even though we have all of this training data, low resource languages simply have a lot less data. So you're dealing with essentially a massive data imbalance problem. And so you can do effective data augmentation, like back translation is a very widely known technique. But the problem of back translation is that the quality is not very good because it's artificially generated data. It's data augmented data. So when you train on all of the silver data, you have a bunch of noise. So as you can imagine, if you have your input sentence and your output translation and it's not perfect, essentially you're teaching the model to hallucinate. So maybe a 2023 analogy to this is like, you're doing fine-tuning on your model for language modeling, and you're using your supervised fine-tuning data, and you're actually teaching the model to hallucinate because it's not perfectly annotated. Like, that's essentially what's happening here. The other issue is that we need to prevent language interference. So yes, models have a large amount of capacity, but when you're trying to model like so many different directions and so many different languages, they can interfere with each other. And that's where the scaling part comes in, which is the third aspect. So if you're not super familiar with how machine translation models work, but you know how language models work, language modeling is just like the bottom half here. So our machine translation system is a transformer-based encoder-decoder model. So roughly like the choral input text comes in, it gets encoded into a transformer encoder model, and then there's an attention mechanism between that and the transformer decoder, which will produce word by word the output translation in yellow. And so if you take all of the data that we created through our mining systems and also this seed data, which is a special training data set that we actually annotated to get like very high quality training data, this is roughly your distribution of training data over various languages. And so the y-axis is the number of sentences, so higher is better, and the x-axis, the list of different languages. And so you can see it's hugely, hugely imbalanced. So if you just train on this right now, what the model is going to do is it's going to produce some great French and Spanish translations. Pretty much everything else will be drowned out, and it will massively overfit on those languages, which means that it can't generalize at test time. And so what we then did was we added a lot more of our mine data. We also did many different iterations of back translation and had a lot of filtering and noise removal mechanisms to identify what is the best back translated data, which is covered in the paper. I'll skip it here to stay good on time. And so you can see this technique like really balances out the amount of training data. So it becomes more uniform, and it's easier for the model to generalize at test time with this. We also explored scaling and reduced interference using mixture of experts architectures rather than dense scaling. And so we used a token level mixture of experts, which means that for each token, the model can access a bunch of different experts and decide which ones to activate. And this enables the different experts to specialize. I will say, like, when we started working on this, there's always the dream that, like, okay, there's going to be a bunch of different experts. Like, one expert will be like the Cyrillic expert, and one expert will be like the Latin expert, and another one will cover like Chinese and Korean. I think that's more of a pipe dream. It's not so much reality, but having different experts, there is some limited specialization. One problem with mixture of experts is that you've added a huge number of parameters, which means that the capacity becomes extremely easy to overfit, which is also a generalization problem. And so one of the ways we deal with this is through a curriculum learning approach. And so some language pairs just have a ton of data, and others have very little. And so what we did is that we trained a vanilla dense model. Then we looked at the learning schedule, and we measured when specific language pairs started to overfit. Then we basically bucketed them. So we were like, okay, here's 4 buckets, like bucket 1, bucket 2, and so on. And then we started training on a schedule. So all of the high resource languages, they train from the very beginning because it requires a full training time to converge on all of the Spanish training data, for example. But a low resource language like Santali, we introduce at the very end so that it doesn't overfit and memorize all of the training data throughout the entire training process, but it still gets to converge. So I want to compare some results now. So this is on the Flores 101 data set. The reason why it's on Flores 101 is that it's the only data set that has previous work on it. Flores 200 will show next. And so what we want to do is the columns, like the first column is translating out of English into the language, that's XX. The second column is translating from the language back into English. Then you have like all cross pairs. So for example, Bengali to Chinese would be like XXYY. And then the last column is the average performance. So if you look at the first set of rows, this is on 87 different languages. There were 2 different works prior to this that evaluated on this set of 87, M2M 100 and also DeepNet. So the metric we're showing here is blue, which is a measure of translation quality, regardless of how controversial it is. So the first number is on word level, and the second is on character. And so you can see the performance is significantly better than existing work. Now we expand to 101 languages. Similar, the Delta LM paper was state of the art at the time from Microsoft. And you can see that NLB 200, even though it covers double the number of languages, it gets significantly stronger performance across the board. We can also check on Flores 200, which is the full set of 200. So you have, again, like you're translating out of English, translating into English, the cross pairs, and the average performance. And we've bucketed them into various different languages. Since there's no real other translation system that has a comparison. It's a little bit difficult to take these numbers into account, but roughly like a guide is like if it's above 30, it's like pretty reasonable, and people can start using it reliably. So you can see that most of them are doing well. Of course, it's still difficult to translate all of the cross pairs. So low resource cross pairs like Icelandic to Santali, for example, still remains challenging. I want to talk a little bit about evaluation as well. And so all of what I just showed is automatic metrics. So they're super great for research iteration, very fast. Like we wouldn't be able to do research if we could only do human evaluation. But ultimately, translation, it's a consumer-facing application. And what really matters is how people who speak these languages feel about the translation quality. And so this is what we did in human evaluation. So this is a limited sample, just to kind of fit on the slide. So the y-axis is what we call the XSTS quality score. It's a number that goes from 0 to 5. The y-axis here actually represents the delta between two systems. And the x-axis here is a bunch of different combinations of different translation directions. So you have gray representing translation into English, green as translation out of English, or sorry, non-English pairs, and then blue as out of English. And so this was the previous, our baseline system compared to our final system that we released in open source. So you can see the amount of improvement is pretty large, and it's also detectable by humans. And you might ask, okay, what is the statistically significant delta? It's about 0.2 to 0.3. And so you can see that most of them are actually statistically significant. So I want to say a big thanks to everybody who worked on this. It was a huge team. The other thing that I'm quite excited about is actually this system powers a Wikipedia translation today. So if you are a Wikipedia editor, as you know, there's like more than 300 different Wikipedias in all sorts of different languages. One of the fastest ways to grow Wikipedia articles in a new language is through what they call content translation. But they had a lot of Wikipedias that were not supported through any translation system. And so we partnered with the Wikipedia Foundation to provide this translation system, and it powers a lot of translation today. So if you're an editor, so for some languages, it's the only system, but for others, you can choose it from the dropdown. You want to choose Flores. And of course, everything is open source. You can check it out on this GitHub repo. Thank you so much.